Hello everyone, welcome to this webinar on seismic analysis in FEM-Design. My name is Flaviu Popescu. Today we're going to use GoToWebinar. And please, if you have any questions, use the question section in your GoToWebinar window and type them here. We will go through them at the end of the presentation, and hopefully we will get to answer all of them. My colleague Mohsen will try to help me with the questions, and hopefully we will get back to everyone. Today we're going to look at the seismic analysis in FEM-Design 17. So I'm just going to jump to my model that I have prepared today, which is a frame structure. I have in FEM-Design. I have defined the geometry. I have some loads assigned to it. I have some self-weight, some snow, and some technical installations, loads, load cases defined. Then I have some load combinations as well. I have some wind loads created by the wind macro, which I'm not going to go into detail in this webinar, but there are other videos to show you how to do this, how to generate wind loads automatically using the wind load macro. To get into the topic of today, which is seismic analysis, I'm going to go through the steps of performing such an analysis. We have the structure, and first thing that we have to do is to define masses. These masses can be defined here in the loads tab under the dynamic load tab. We can either define masses manually using this mass definition tool, and you can just define masses in tons and place them on the structure. This is a manual way to define the masses. Another way is to convert the load cases into masses, which is the case in this example as well. If I go here to convert masses from loads, I have the load cases which I have defined, and I can use a factor to convert the loads into masses. I have here a factor for each of the load cases, and I have my list of load cases. I have transformed the vertical forces into masses using these factors. Just keeping an eye and making sure that the sound is okay and that the image is okay, and it seems fine. Okay, so I have my masses defined. While I'm here in the loads tab and being in the dynamic loads, I have here the tab for the seismic load. Here's where I define my seismic load as spectra. I can enter here the structure information, the building structure or non-building structure. And here is where I have my horizontal spectra and vertical spectra. This is where I define the seismic load. I have here some predefined types. The ground acceleration in meters per second square. And I have the periods. I have the behavior factor and the beta value. Now this is how I can define the spectra with these type of settings. I can also define the vertical spectra if it's the case. There's also the option to do a unique definition where I enter manually my period and my acceleration, SG. So I can enter them as coordinates and the spectra will be generated in this way. I also have the option to save this spectra and load spectra from different projects if I have one made already, and I can use it for several cases. But for now, I have defined these spectra for my seismic load. Having the masses defined will allow me to perform a eigenfrequency calculation first, which is the first type of calculation that I will make. I have already made it, but I can just select it again. Here in the Calculations tab, I can enter the number of shapes that I want and click OK. I also have the option to select the top of my substructure. In this case, it's 0 meters, and the masses on this level and below are not considered in the eigenfrequency calculation. So this is the top of my substructure. Click OK, and I will have a eigenfrequency calculation. It's good. I see there's some questions. We'll get to them at the end of the presentation. I have now made my eigenfrequency calculation, and I can see my results. From the analysis, I have the eigenfrequencies. I can see the nodal masses that have been generated and the total masses for each level. I can see here the total mass being of that value. This is the mass that will be used in the seismic analysis. I also have different vibration shapes for translational displacements and rotational displacements. I have here each vibration shape with its characteristic frequency and period. For each of the shapes that I selected, in my case, it is 120. So I get these results from my dynamic calculation, this eigenfrequency calculation. Okay. Having this eigenfrequency calculation, I can now use it to set up my seismic analysis. I go to Setup, and here I have my seismic analysis setup. I can see the type of analysis that I can perform. I have static linear shape, static mode shape, and modal analysis. I'm going to focus on the modal analysis in this presentation. For this, I have to take into account the mass contribution for my structure. So I have to select the contribution of the masses for my shapes. I have done that already, and I can use it. I have also some settings here, summation rules by directions. I have the two cases, the two types of the summation rule from my analysis. I'm going to use this one, and I'm going to perform the seismic modal analysis. now have results for the seismic analysis. I can see here that I have equivalent loads. I can see here that I have the equivalent load from my seismic analysis. Then I have translational displacements, rotational displacements, accelerations, reactions, connection forces, and bar internal forces from my seismic effects. So I can see the results on my structure according to the seismic effects. Now I have the seismic analysis, I have the eigenfrequency calculations, so I can actually include this seismic effects into my fundamental load combination. In loads, under load combinations, I have already defined this type of load combinations, and I have included the self-weight, the technical load, snow load, and then this seismic max load case, which has been generated from my seismic analysis. Of course, I use the factors which I want for the combination and make sure that my load combination is set. I can then go ahead to analysis, perform a load combinations. Now I can go ahead and look at my results from a load combination analysis. If I want to look at bending moment My, I can see it on my structure. And I can also see, for example, if I want to check my columns and see the bending moment at the base of my columns, I can just select for a better view columns. Increase the scale. Maybe I can also see it for each of my column. So I have the forces, the internal forces from my seismic analysis with the fundamental load combination. Of course, after this analysis is complete and I have my forces, I can go to the design tabs and design my structure as I would using these forces. I think this will be a short webinar today. I think we should take questions if there are any here. Let's see, is it possible to design structure to DCM and DCH as defined in EN 1998? Ari, I don't know exactly what DCM and DCH are. Maybe we'll get back to that question. When I was trying to make a seismic analysis for one-story building, I have at least 2 stories. Well, what I have here are 2 stories. I need to define this first story and then my second story. So I need to have 2 stories defined, which will set the bottomest level and then the top level. And these are important when setting that top of the substructure for to be considered for the masses to be considered above that substructure. So I need to have 2 stories defined here. I have here the first one up until 0, and then the second one up to 10.5. So I do need to have 2 stories defined. And this is how you can do it. How do you define at the beginning the loads? The loads, the simple loads are just load cases here. You just define your load cases. I have defined these types, self-weight and snow, and then wind. And then the seismic loads are generated from the seismic calculation. Ductility class medium. Yes, this is what DCM and DCH stand for. I think that's yeah, that's up to you how you would design it. This is you perform the analysis here with your parameters, and then you design it according to your ductility class. I'm not sure about this question, Ari. I'm going to look at it. I'm going to take a look into this and then get back to you to get a comprehensive answer. The factors under the dynamic load. The dynamic load. So you have the seismic load, which you define here with the spectra. And then for the seismic analysis, you define it here. You have several options here. Add the combination rule and take into account the torsional effect for buildings. And then you also have this combination rule where you can get signed results, have the option to get signed results. I don't know if this is what you meant, Louis Anderson, to define the factors under the dynamic load. Yeah, you define them here for the for each load case when you convert to the mass, when you convert load cases to the masses. This is just my choice. This is just my choice that I chose 0.4 first now. I can also choose it 1, for example, or 1.2. The design of the elements is in the RC design tab and the steel design. So I can perform an RC design according to those, to my results. So I can define the, I can design the reinforcement bars for my concrete elements and design my steel profiles for the steel. It's basically using the design modules. So this is how you design the elements in FEM-Design. According to Ian 1998, I'll have to see about that. So I guess I will come back to this question, Anna. Steel design works as auto design. So this is where you design your elements. Oh, sorry, this is for concrete. For steel here, you have the automatic design, which lets you choose from a list of parameters and then checks the design of the elements. I'm not going to perform it now. It's well, I can actually, if I choose design here, I get that the design for these small steel elements. They are mostly concrete, the concrete columns that deal with the moment from the seismic analysis. And then, yeah, the program suggests a element, and then you use that and get the results for that. Yes. Romel, for vibrations only need Eigenfrequency. And you define your masses for that. Please check out our YouTube page, our YouTube channel, where we have webinars regarding FEM-Design, including the design of steel elements and concrete elements. See if I have it here. Soft official. This is our official YouTube channel. And for FEM-Design, we have some playlists here, including the FEM-Design webinars. It will show you more about our FEM-Design program. Also basic courses, basic introduction of the functions, of the basic functions in FEM-Design. To those of you who are not using the program at the moment, or not using the program yet, we have trial licenses, and you can find them on our beautiful new webpage. If you go to strusoft.com/products, FEM-Design, and get started with a trial license. Then fill out the form and apply for a trial version. Okay, I think I will stop here if there are no more questions. Also, if you have questions later on, you can contact me at this email address or just call me at this telephone number. I am located in our Denmark office in Copenhagen, our StruSoft Denmark office. All right, thank you very much for attending today, and I wish you a pleasant rest of the day. Bye-bye.